Hello everyone and welcome to my talk, which is the second talk in process of my habilitation. Today I'm going to present some recent studies that we did on end-to-end adaptive video streaming optimization. This agenda that we planned for that: introduction, degree of freedom in video streaming, what's the definition of that, and brief review of recent studies and future research direction, and followed by the conclusion. One slide for me that, as Christian said, I'm a postdoctoral researcher here. I joined Athena in 2021, and my previous position was the assistant professor at Azad University of Mashhad, Iran, and I got my PhD in computer engineering from Ferdowsi University of Mashhad, again Iran. And this is a list of my research interests. First, I work on the computer networks, different features of the computer network, software-defined networking, network function virtualization. But my main research topics here: multimedia system that cover different range of the things in multimedia streaming, multimedia networks, real-time video streaming, until the quality of experience. So, I'm working on the Athena project, and it's good to first introduce the Athena project. Here is one slide that is about the main building blocks of the Athena project. We have, in the Athena, we have these 4 modules: content provisioning, content delivery, content consumption, and one wide block that covers these 3 sub-modules that end-to-end aspects. Each of these modules, as you can see, have its own research questions and topic that we need to work on that. And we need to address different things, different problems, different parameters in each block. I mainly work on end-to-end aspects in this project. Based on these building blocks, we can dive into details of the modules that we have in each block. For the content provisioning, we have different sources, for example, live camera and video on demand, that based on the different softwares we have, we need to encode them and prepare them and push in the origin as an ingesting component in the video streaming. And then we have the content delivery to push and to deliver all content to the edge, and then at the content consumption, we have clients that consume this data in information. And as you can see here, we have the wide range of the block here that is end-to-end aspects that cover many things inside these 3 blocks. This is a horizontal view of the video streaming. And based on this definition, we have also vertical view of the video streaming. In vertical view, we can refer to the revision model that we proposed, and we introduced this revision model, this revision that in the first talk of my habilitation, that includes the different layers. For example, here we have application layer. Inside the application, we have some objectives, for example, QE, cost, and latency. Also, we have some constraints that is coming from the application layer. For example, the content type, user mobility, and desired constraints. For example, those constraints that limits on the cost on QE or latency. And also we have some applications that are related to the video streaming. For example, encoder, decoder, transcoder function, ABR, different things, different functions that we have in this layer. Then we have control and management layer. In the control and management layer, we have one main and primary module here that includes optimizer, coordinator, and scheduler. And also, we have 2 main components that are related to the one is application control that is correlated with the application layer. It includes application monitoring, application analyzer, and also we have one controller that covers the resources that we have as resource controller. These modules are connected to each other and are coordinated by this central module here as a coordinator. And last but not least, we have resource layer. Inside the resource layer, we have 2 main sub-modules. First, resource type, that is simply we can say computation and communication and storage, and also we have resource cost and availability. That is about all things about the resources that we have in terms of the ability, in terms of the cost of them. And through these layers, we can have a vertical view. And if you want to work on the video streaming, you can consider this model that explains the details of the video streaming. And in the first talk, also we introduced triangle of the video streaming that we elaborated here, this model that in the video streaming optimization, we have a triangle. That the first and foremost is that objectives that we have. We have three main objectives: cost, QE, and latency. We need to optimize them in all, I can say, in all applications of the video streaming. Also, we need to consider the input space. The input space means that from which parts of the network, of the edge, of the origin or the client, we need to consider some parameters. This is a list of the parameters that we have in the software stack, in the application or resources. And then we need to define our action. We need to apply our action on some part of the pipeline of the video streaming. So this action is about the distribution or contribution or consumption part. So what's the degree of freedom in video streaming? I think that is a good slide to demonstrate how we can apply our ideas on video streaming. In the one line, in the pipeline, we can see that, for example, here from the live and from the VOD, encoder, ingesting, reach to the disk client side. All components that we need can be placed in this direction, okay? So what's important for us, cost and latency, is two main parameters that we are worried about that at the client side. And we usually measure them during the streaming to apply some appropriate actions on the pipeline. And the cost also is another parameter that we can say that cost is related to all parameters here. And then by measuring that parameters at the client side, we can say that, okay, based on this information that we have, we take an action that can be applied on the client. For example, we can fix some problem in the ABR algorithm, or we can apply some actions on the network edge. Also, we can apply our solutions on the distribution network, and also we can make a more distance from the clients and apply our action on the ABR encoder or on the origin side. I think that this is a degree of freedom that we have in the video streaming, where we want to apply our actions on the pipeline. And then, by taking distance from the source, the efficiency is enhanced, but we have to meet some challenges here. Because we need to, for example, if we want to apply our actions on the ABR encoder, we need to consider many components and adjusting and collaborate with the different items on the pipeline. So based on this category and this definition, I listed all works that we did, some of them that just focus on the client side. Those papers that study some solutions that we need to apply on the client side, for example, content consumption energy measurement dataset for adaptive video streaming, or Coconut, H2BR, that's the one of the ABRs that we proposed here, Medusa, EVish, and DOF+. These are some of the works that I listed here. And today I'm going to just focus on the Medusa. What's the Medusa about? Before starting introducing Medusa, first take a look on the main research questions that we have here and we addressed based on those researchers that I highlighted here. For example, how we can design the energy efficient ABR algorithm. We addressed this problem with Coconut and EVish. How can the new feature of the new protocols can be leveraged in the video streaming? For example, H2BR and DOF+ address the problem. And how can different codecs enhance the QE at the client side? Medusa is one of them that we address here. And these are the main objectives: QE, latency, and the energy and the cost. And also the key elements of our proposed solutions are about we introduce one, for example, ABR algorithm or mathematical optimization, or we leverage different protocols in these studies. So for the Medusa, the main motivation is introduced in this table. In the web browser, we have different web browsers, okay? And this is a market share of these browsers. And also we can have this list of the supported codec by these browsers. Why we have different different flavors of these codecs? Because different codecs produce segments with various size and quality. So we need to consider them during the streaming and which one is the good at that moment. So in the first step, we defined and we modeled this Medusa in the central manner. And we, for example, consider that we have a media or CDN server that includes many, for example, codecs, assets here, different representation, different segments. And then we have one normal ABR that just playing and just working with one, for example, codec here, AV1, that start streaming with that one. However, if we want to implement one new approach and let the clients to have to fetch different codecs, for example, client B that support multi-codecs here, okay? So we received all URLs and some information from the clients, all clients that want to support, for example, multi-codec, and then we offer them which codecs good at that moment. But it's very, its time complexity is very high. We cannot apply this approach on the real video streaming, real scenario. Then we came up with the one heuristic algorithm that we try to scatter the complexity on all players, not just on one component in the edge. So here we shift or we push this module, is a version of this module to the clients to help the player and specifically ABR, and offer that player that which codec is good to at that moment to fetch from the server. So you can see here, for example, we consider different content and different ABRs here, those that enable with the Medusa. And you can see here the average transmitted data is, the average transmitted data, okay, is lower than the original one. And also you can see that the QE goes up here. For example, for all ABRs, it means that Medusa could help the ABRs to perform better. So in the next group based on this degree of freedom, we can consider those works that apply on the distribution network and network edge. Here we have different studies here, but I listed here just some of them. MCOM Live, CDLWT just is one of our work that is better to say that the family of LWT. And the OSCAR also, we have one journal of that and one conference on that. And RUPL, another one, MAQVC and S2VC. There are many works there, but I just selected them to highlight them. But here, because of the time that we have, I just focus on these three papers here. Again, before starting those research questions that we address them during this years, just how, for example, how can the network assist the video streaming applications, for example, with that work, we address that. And how can network edge resources can be leveraged to enhance the QE, also those work. And the last one, how to enhance the QE by some emerging techniques in the network, those papers. And the main objectives, again, QE end-to-end latency and the resource cost. And these are key elements of our proposed solutions. AI and ML techniques, mathematical optimization, leverage different methods in the network, SDN, NFV, and traffic engineering, and optimal resource allocation to the stream. Here first, take a look on the LWT family. That first one is that published in the IEEE Access is about the main idea that we had, and the motivation is that because of the time and computational tasks that we have in the encoding process, we do some search task during the encoding. And the motivation is that why we need to spend time on the encoding process every time that we need to, for example, encode something to the some quality to another quality. Then the idea is that, okay, we can save the research results, we can save the search results during the encoding process, and then by sending them to the edge as the metadata, we can leverage those metadata and the search results to apply on the new encoding process. The solution is that just based on the mathematical optimization, we first try to find out the behavior of this model, and then by having that, we propose the heuristic algorithm because of the gain of the complexity. And then results showed that we reduced the transcoding time by 80%, and also we had some improvement on the storage and also on the computation. The next version of that is CDL ability. That CDL stands for the cost that we consider here. Actually here, we consider the cost of this storage or storing the at the edge server and transcoding the computation that we need for transcoding and fetching. Here in CDL ability, we consider the cost and we consider the delay also. We need to take a good action based on the request from the client side. And in the CDL ability, we showed that, for example, we could reduce the transcoding time by 97%, and it's very good at that moment that our work impact on the transcoding time, because transcoding is one of the modules that in every stream, all streams I can say, we have this, and the time of transcoding is a matter for us to decrease that. And decrease storage, computation, and bandwidth costs by up to 75%, and reduce delay also by up to 48%. The another work here is RUPL, that is about the quality optimization of the live streaming services over HTTP with reinforcement learning. Here, this is a module that we created on the edge. We have the players here, we have our server here, and this module is implemented on the edge, on the network edge. We try to address the same question, the same research question here by just working on the AI techniques, AI learning-based techniques that let us have different tastes of the solutions in the video streaming. For example, here in RUPL, we use deep reinforcement learning, proximal policy optimization, or PPO, to manage all requests here. What's the story about that? Here we have many requests that are coming from the players, okay? And then in this module, first we categorize them based on the live channels that we have. And then in each live channel, we have different queues that is based on the qualities that we receive from clients. And based on this information that we have, also based on the bandwidth that we have on between the clients and the server, we decide to, okay, fetch from the CDN origin, or serve with the lower bitrate, or serve with the transcoding, or do nothing. Based on the resources that we have, sometimes we can select, okay, we don't need to take action here. We implemented this idea using the servers in the university in campus, and we showed here, for example, with 100 players and with 8 megabits, for example, the bandwidth that we allocated them. Just the average of the queue, you can see that this blue one is about RUPL, and the VRP and direct also these two colors. VRP means that we have only one reverse proxy, virtual reverse proxy that receive the request and try to fetch from the server without any consideration of these modules that I presented here. And direct, it means that we can omit this module and let the clients directly connect to the server and then fetch all requests from there. Okay, so here, based on this map that we have here, roadmap, we need to cover some works that here we target the origin site. And based on some feedbacks from the clients, we apply our action on the origin site. Here, the list of list of the papers that we have here is Artemis, Adaptive Bitrate Ladder Optimization for Live Video Streaming, that is got accepted by NSTI 2024. And Adaptive Bitrate Ladder Optimization in HTTP-based Adaptive Live Streaming, or LaLISA, in NAMS, and HXL3. There's a framework for optimizing live streaming, Journal of the TMM, or Transactional Multimedia, and CocoV, Elsevier, ComCom, and Koala is the one conference paper that got accepted by LCN. So here, let me just focus on these two papers that somehow they are related to each other. Again, the main research questions that we have here: how to design a scalable and practical end-to-end approach that HXL3 addresses this one. Which parameters should be collected from the clients and the origin side to optimize the live video streaming? Here, Artemis and LaLISA, these two works that address this research question, and how to design framework for user-generated content application to enhance the QE of the clients, CocoV and Koala. Again, these are main parameters, main objectives that we consider here. For example, QE, end-to-end, latency, and the cost in terms of the resources that we have, and also with energy. The key elements are AI and ML techniques. As usual, we have some mathematical optimization, leverage some emerging techniques, for example, SDN and NFV, traffic engineering, and optimal resource allocation. Okay, so based on the simple description of the video streaming, that we have a live camera here, and then the content using, for example, RTP protocol reach to the one origin server, and here, based on the given bitrate ladder that we have, we try to encode them in the different segments, and based on this, information that we have in the bitrate ladder. Here, after preparing those segments and manifests also, we push them to the CDN server, and this information that all segments and manifests lets all clients connect to the CDN server and start streaming. So this manifest includes a representation based on the clients have this freedom to, based on some measurement of the bandwidths or other information, select one representation from the CDN server. And then with the HTTP request and HTTP response, they start streaming and playing the video. Okay, based on this description here, the question is how to construct an efficient bitrate ladder to enhance the QE, not just for the VOD, because for the VOD, we have different ideas about creating an optimal bitrate ladder. But for live, it's very challenging, because in live, we have a fluctuation in the network, we have preparing the content, and we don't have time to make or to apply the best encoding bitrate ladder in the origin server or in the encoder. So in the LaLISA, the LaLISA is the one paper that I presented in my first talk, that at that time I mentioned that this LaLISA has some issues, for example, scalability, because we applied some changes on the player side. And we changed the player, and then we forced player to send desired bitrate to the CDN server. But here, this scalability issue pushed us to have propose a better idea here. We presented Artemis that addressed this scalability issue, and here we introduced the mega manifest for the first time in the domain of the video streaming. As you can see here, we have one mega manifest that consists of many representations not real presentation. I can say virtual presentation that's not encoded at the client side, at the server side. But we have this mega manifest, and then we receive some information from the clients to the content delivery network, and using these logs, we have Artemis Analytics server that fetch these logs and extract the good information, useful information from them. And also we have the Artemis origin that connected to the origin server and extract some information from the encoding process, during the encoding process. And exchanges messages to each other to find the best or optimal, I would say optimal solution for the ladder. So the main idea is about this mega ladder, mega manifest. This mega manifest, you can see there are many bit rates here. For example, with the small gap between each in terms of the bit rate, or maybe in terms of the VMAF here. So based on this mega manifest, we let clients have a better selection or better decision on the next bit rates. We don't want to limit the clients based on the small manifest to just see this, for example, 5 representation, and they have to select 1 from 5. But imagine we, for example, offer them more than 30 representation, and they can have this freedom to select the one that is the best for them at that moment. So, but this mega manifest doesn't mean that we need to encode all of them at the origin site. Encoding the all content of manifest is not something that is practical at the real scenario, in the real scenario, because it's very time consuming. Because we need to spend more high computation, and also we need to, for example, run multiple encoders to encode all representation. Is not very useful and efficient way, because also if we need to, for example, if we want to encode all of them, we need to have a high bandwidth to push all the contents to the storage and the CDN server. So what's our idea here? In this slide, I try to give you the Artemis in one picture. For example, here we have this mega manifest at the CDN server, and then clients receive this mega manifest and start their streaming based on the all representations that we offer them. And we receive their all requests by the CDN server. As you know, CDN servers can send some logs to us for some processing, and we gather them, we collected all of them, and also we receive some information from the origin server. For example, some metrics during the encoding process, we received them, and then we created OTL, or optimal temporary ladder. Based on the all requests and the frequency of requests in terms of which quality they are interested to get, and also based on the some metrics from the client side, we design a optimization model that determines which bit rates is suitable at that moment. Maybe in time slot, which one is the suitable to serve the clients. So here, if one client select this one, then we don't have it, but we can send this one as a lower one. And we try to have the lowest, we try to keep the lowest one here for those clients that join the network and try to, for example, reach to the minimum one, then we can offer them. There is no transcoding here, just we try to come up with the good algorithm to be applicable in the real scenario. And then we can utilize this OTL at the origin site, and based on the content at that time that we receive from the live camera, we encode the segment and we push them to the CDN server. So this is our test bed. That this work just is about a 1-year work on this paper. I would say that we have the clients here, media players, and then we have this AS server that implemented on the one EC2, and also we emulated the CDN front end here. on the Amazon, and also we use the Bitmover live encoder to connect to the AO agent and fill out these tables and send this information to the OTL and then to the AS server, and the AS server send back this optimal temperature ladder to the live encoder. And we run more than 15,000 video players on Amazon during this research, and based on the statistics and all data that we collected at that time for different type of ladders that already we have them in the industry, for example, TEO, Bitmovin, Max, Pensive, Twitch, and Artemis. As you can see here, in Artemis we prepare all of them. We offer all of them to the clients, but not really encode them, but just offer them. But you can see, for example, Bitmovin or different ladders here offer just only a subset of them that they are encode them and prepare them for the clients. Here, these are three graphs that represents the, for example, the improvement that we have over the QE, for example, up to 11% based on the different network trace, LTE, Amazon FCC, and Cascade, with 5 seconds of duration of the fixed bandwidth and also 20 seconds of the fixed bandwidth. This bar shows that how much we improve the, for example, how much Artemis improved the quality regarding TEO. For example, for the TEO, we improved about, for example, 17% for the Bitmovin, for the Max, Pensive, and Twitch. And you can see, for example, in Cascade 5, we reached to this 34% improvement, for example, in Max. And for the latency, you can see that we improve also latency, because sometimes we send some information with the lower quality and let them to have a better and a smooth streaming, don't have many stalls during the streaming. And we reached to the, for example, 18% on average, and also the stall 36% that we reduced the stall. Okay, so for the future research directions, here I selected 3 main directions for the future that I like to work on them because of there are very interesting problems and very promising results we have during these studies that we are doing. For example, energy efficient video streamings. Based on some reports, IEA, for example, stated that end user devices are responsible for the majority of the energy consumption, about 72%. That followed by the data transmission and the data centers. That's very important for us to tackle with these problems that we have on the client side because of the numerous number of clients that we have. And generative AI in the video streaming also is another direction that I'm going to work on this. Why? Because we can, based on the AIs that and the algorithm that we have, we can reduce some cost and also requirement that we need and increase the QE. I think that in the future we can say that we have the video streaming, but not actually by fetching the segment, real segment. We just have, for example, some text from the server side, and then we generate the content for the clients based on those texts. And the last but not least, optimize immersive media streaming is something that is very challenging, domain, because we have many challenges here. For example, those challenges that we have in the normal streaming, also we have more challenges or more problems here that is about the type of these applications that we have is immersive, and we need to have, for example, high bandwidth, low latency, and try to give the user the good feeling that is a part of the streaming, is the interaction with the media. And the conclusion is I introduced the vertical and horizontal view in the video streaming, then about the degree of freedom in video streaming, and what's the definition of degree of freedom. I think that is very important for the researchers to know about how they can apply their solutions, apply their ideas on the video streaming, because as you know, there are many items, many parameters. I try to categorize them and to give a roadmap to the researchers and the students. And brief review of the recent studies that I selected, some of them. There are some works that I didn't put them here, and presented future research directions. This is a list of the papers that I didn't put in the slides, but I try to highlight them. Some of them is very good. For example, this work that we did about the DigitWise with my colleague here at accepted in MMCs, and they are based on the collaboration with my colleagues and different universities and research institute that I tried to add this slide, and thanks all of them too for their nice collaboration and help and support me during this time. And they are from different universities and research institute that I put it here, and thanks all of them. And thank you for your attention, and I'm happy to answer your questions here. Thank you.